Let me introduce you to our project, 3D Human Activity Recognition, or 3DHAR-AI for short. The growing field of HAR sees many applications, from remote health monitoring for the elderly to smart homes that adapt to our daily routines. In our work, we investigated the performance of 3 state-of-the-art spatio-temporal graph neural networks against traditional deep learning models, setting clear performance benchmarks. We also extended this to human activity prediction, looking at not just what someone is doing, but what they're likely to do next. Finally, we built a 3D virtual environment that lets us visualize sensor data in real time. This environment can be used for data augmentation, the generation of new training data to help future researchers build more accurate and robust AI systems.
The motivation for our research into SCGNNs for this task is due to the fact that while traditional models like convolutional neural networks and long short-term memory networks achieve strong results for human activity recognition and prediction, they capture only temporal patterns, ignoring the spatial relationship between sensors. SCGNNs address this by jointly modeling spatial and temporal dynamics. Sensors in a smart home can be viewed as a graph, and SCGNNs can be used to learn the relationship between these sensors and how they evolve over time. SCGNNs also come with the advantage that their learned graph structures can be extracted to reveal insights into human activity. The SCGNNs we tested did not outperform the baseline models and required significantly longer training and inference times due to their complexity. However, SCGNNs are still useful for this task as their learned graph structures reveal prominent pathways of activity flow.
We will now introduce our novel data augmentation strategy involving a custom 3D environment. We use this strategy to perform HAR and HAP to see if we could experience performance gains whilst reducing financial and time costs of recording human activity data. This short demonstration demonstrates what the environment looks like and how the agent navigates it automatically. To augment the dataset, firstly, we warp to a desired location, then we press pause, then record activity, as well as selecting the desired activity to be recorded. We then choose this and record this activity by activating sensors. As you can see, for HAR, we observed substantial performance increases, with the highest being nearly 10% change in weighted average F1 score. We did experience more variable results for the more difficult HAP task, but this strategy shows promise for future refinement and work. In essence, we created an AI-driven approach to HAR and HAP using state-of-the-art methods, as well as introduced a novel data augmentation strategy to investigate the performance and practical benefits associated with it. Thank you.